Okay, so let us continue with our discussion about Moebius transformations. So you see, yesterday I was trying to tell you or rather in the last lecture I was trying to tell you that a Moebius transformation is it going to AZ plus B by CZ plus D with the condition AD minus BC equal to 1 is called parabolic if A plus D the whole squared, which is actually trace squared of the matrix ABCD is so the trace squared is equal to 4. Okay, so this matrix ABCD is a representative of this Moebius transformation in SL2. Okay, of course the other representative is minus A minus B minus C minus D, alright, and if you take the trace, it will the trace squared, it will be the condition that it is 4 is it will give you the condition that it is parabolic. In fact what I proved yesterday I mean in the last lecture was it's parabolic if and only if this is equal to 4 if and only if it is conjugate to a translation. Okay, so this is what I proved yesterday, alright. So in particular and of course let me recall so maybe I should modify this. I should not say it's called parabolic, is parabolic, if and only if this condition holds, and of course parabolic means only one fixed point in C union infinity. Okay, so a Moebius transformation, you know, if it's not the identity, okay, if it is the identity it will fix every point, right. If it is not the identity it will have at least one fixed point and maximum it can have two fixed points, right, and the case when it has only one fixed point is the case which is called parabolic, alright. And the point I wanted to say is that this parabolicity condition translates to a condition on the trace squared, and that trace squared has to be 4, alright. So you can see that the way this is going, the classification of Moebius transformations is being done in two ways by thinking along two directions. One is by looking at the number of fixed points, the other thing is by looking at trace squared. Okay, so let me look at the other cases, right. So suppose a Moebius transformation is non-trivial. Okay, so it is not the identity transformation and has two fixed points. Okay, so the case when it is one fixed point is called parabolic. The case when, so what is left out is the case when there are two fixed points. Okay, so this is a non-parabolic case. Okay, now what does how do we classify Moebius transformations which have two fixed points? Okay, so the key to this is again looking at the values of trace squared. Okay, so suppose the Moebius transformation the Moebius transformation is given by z going to a z plus b by c z plus d as usual with ad minus bc equal to 1. Okay. So again the point is to look at the values of trace squared of the representing matrix in SL2, alright. So you see we say it is a loxodromic, okay, if the trace squared ABCD, which is a plus d the whole squared, okay, does it does not be, so this is a complex number, mind you a b c d are complex numbers, alright, and in general when I calculate a plus d the whole square I will get a complex number. What I want it to be, I want it to be a complex number which is not a real number lying from 0 to 4, okay. So this belongs to the set of all z in C such that z so I should say z is not a real number in with 0 less than or equal to z less than or equal to 4, okay. So this is the condition, alright. So so you know if I try to draw a diagram, I have the whole complex plane, okay, and then I have this line segment here from 0 to 4, I have this line segment, alright. If so this is the line segment here, okay, and if your trace, if you calculate trace squared and does not, that value does not lie on this line segment, okay, that is it lies outside the complement of this line segment, okay, then it is called loxodromic, it is called loxodromic, alright. Notice that if trace squared, so what is left out is the case when trace squared is real and lies between 0 to 4, okay, that is what is left out. So that gives you two other cases. So so let me write this down, it is called hyperbolic. So let me first say elliptic if trace squared, which is a plus d the whole squared, is real, okay, and it lies between 0 and is strictly less than 4, okay. Of course you know trace squared equal to 4 is parabolic, okay. So this point is parabolic, okay. So I'm looking at here, I'm looking at values of trace squared, which is a plus d the whole square, okay. So when it is 4 it is parabolic, if it is from 0 to 4 but not equal to 4 then it is called elliptic, alright. And of course if it is real and its value is greater than 4, okay, then it is of course loxodromic, but it is given a special name, it is called hyperbolic, okay. So hyperbolic if trace squared ABCD, which is a plus d the whole squared, is real and a plus d the whole squared is greater than 4. Okay, so you see this this region, it's elliptic, not inclusive of the point 4, but everything from 0 up to something less than 4, okay, up to all values less than 4, it's elliptic, okay, and then from beyond 4 onwards, so from here onwards, so it is elliptic, I mean it's hyperbolic, okay. So this is the these are the definitions, okay, and you can see that all these definitions are I mean the definitions are mutually exclusive except for the fact that a hyperbolic transformation is a very special type of loxodromic transformation, okay, and so you have elliptic, so if trace squared is real, okay, then trace squared has to lie, if it lies between 0 and 4, okay, then it is elliptic. If it is equal to 4 it is parabolic, if it is greater than 4 it is hyperbolic, and any other value if it takes, then it is loxodromic, okay. So these are the important definitions, okay. So the point is that these definitions come from looking at this quantity, namely the trace squared of a matrix representative of your Moebius transformation in SL2, okay. So the what you must understand is that this quantity, the trace squared, seems to do the job of trying to classify them, alright. So let us study in detail what these cases are, okay. So well, I have already told you what parabolic transformations are. They are the ones which have only one fixed point and they are essentially translations, okay. But Moebius, a general Moebius transformation consists of various things. I mean you can break it down into translations, rotations and scalings, okay, and of course you can also break it down into inversions, okay. So you can factor it out, right. So we have covered, so the parabolic case corresponds to the translations, alright. The other cases come here, okay. So let's try to analyze this. So let me look at a Moebius transformation of this type. So let Z going to A Z plus B by C Z plus D, let me call this as A, okay. So this is A of Z, okay, be a Moebius transformation with two fixed points, okay. Let us take a Moebius transformation with two fixed points, or let me even begin by taking with it will have if you assume that this is not the identity transformation, it will have at least one fixed point. So let me first take that case, okay. Let this be a Moebius transformation with fixed point Z0, okay, let us say. So and assume A of Z is not A of Z is not the identity transformation, okay. So or rather let me say A is not trivial. A is not trivial means A is not the identity transformation, right. So it has at least one fixed point and it could have two fixed points. Now you see the first thing I want to claim is that if Z0 is infinity, okay, then C has to be 0, okay. So let me write that down. If Z0 is equal to infinity, then I claim that C is equal to 0, okay. Why is that true? because if c is not equal to 0, okay, then I can make the denominator vanish by putting z equal to minus d by c, okay, and if I put z equal to minus d by c, the denominator vanishes, therefore this quantity will become infinity, okay. So that is how the point at infinity is also included along with the operations on the complex numbers, okay. If you remember, any finite complex number divided by 0 is taken as infinity, alright. So if I put z equal to minus d by c, okay, then minus d by c is a finite complex number, okay, it is not infinity and it goes to infinity, okay. So this goes to infinity, okay. Now but you know, all your Moebius transformations are bijective and biholomorphic maps of the extended complex plane onto itself, C union infinity onto itself. Therefore if minus d by c, a finite complex number, goes to infinity, then infinity is not a fixed point, okay, because of injectivity, alright. So c has to be 0. So what it means is that the matrix form, the matrix then becomes you know, A B 0 D, okay, and in fact these are precisely the Moebius transformations which are automorphisms of the complex plane, okay. What are the Moebius transformations which are automorphisms of the complex plane? They are all those Moebius transformations which keep the point at infinity fixed, and for keeping the point at infinity fixed, this is the upper triangular matrix form that you will get, okay. So this Moebius transformations of this type, they form automorphisms, the holomorphic automorphisms of C, and we used to denote that as P delta 2 comma C, okay. So fine, so now suppose so you know, if z0 is infinity, then it is already in that form, but suppose z0 is not equal to is not the point at infinity, okay, suppose z0 is not the point at infinity. So here, by the way, okay, so I will make that remark later. So if z0 is not the point at infinity, if z0 is not the point at infinity, okay, then we can find a Moebius transformation B with B of z0 is equal to infinity. You can do this, you can move z0 to infinity, okay, you can move z0 to infinity. For example, you could have taken B of z to be simply 1 by z minus z0. If you take B of z is equal to 1 by z minus z0, then z0 will go to infinity. So it is a Moebius transformation that will move z0 to infinity, okay. And you see, mind you, the matrix representation is, you know, 0 1 1 minus z0, okay, and if you want a matrix representative in SL2C, I want determinant to be 1, okay. So what you should do is you can change sign everywhere, so I will put minus minus here and I will put plus here. So this is a matrix representative, okay. Does that help? Probably no, it is still minus 1, so maybe I will have to take z0 minus z, right, I will have to take minus z plus z0. If I take minus z plus z0, then it should work. So it is going to be 0 1 minus 1 z, okay. This is now in SL2, right. So just to keep track of the matrix representative, right, fine. So the point is, why I am doing that is because, you know, if you want a matrix representative, you must make sure that it is a representative in SL2, so you must adjust it so that the determinant is 1, okay. Alright, so if I put z equal to z0, B of z0 is going to be infinity. Now watch, if I take B A B inverse, okay, if I take this B A B inverse, if I take this Moebius transformation, namely I conjugate A by the Moebius transformation B, alright, then this Moebius transformation will have infinity as a fixed point, will have as a fixed point, okay. So you will get, that is, and that is because you know B A B inverse of infinity, okay, B takes z0 to infinity, so B inverse of infinity will be z0, so I will get B A of z0, okay, but z0 is a fixed point of A, so A z0 is A is just z0, so this is just B z0, and B z0 is actually infinity, so you see B A B inverse of infinity is infinity. Moral of the story is, if you have a fixed point at z0, I can always conjugate it so that the new transformation after conjugation has fixed point at infinity, okay. So so this means that if I write B A B inverse, its matrix of if I write it out, okay, then the matrix form has to be, it should look like this. So you see B a matrix representative, so in fact let me write this, so B A B inverse is of the form Z going to let me use A prime Z plus B prime by 0 Z plus D prime, okay, because I have already told that whenever for a Moebius transformation, if infinity is a fixed point, then this member, okay, this entry has to vanish, so it will look like this, okay. Now you see, so that is, this is what, this is just Z going to A prime by D prime Z plus B prime by D prime, okay, and notice that D is not 0, because then you know AD minus BC is 1, okay, and since C is 0, AD is 1, so D is not 0, mind you, alright. So dividing by D here or dividing by D prime here is allowed, okay, there is no problem there, okay. So now you see that you know if you put further the condition that A has only one fixed point, suppose I put the further condition that A has only one fixed point, okay, that means A is parabolic, okay, then I claim A prime is equal to D prime and it is a translation, okay. If further A is parabolic, okay, then in the case z not equal to infinity, which is here, A must be equal to D, okay, and you know why this is true, because you know since as I explained in the last lecture, A minus D the whole squared is A plus D the whole squared minus 4AD, alright, and well A plus D, if it is parabolic, A plus D the whole squared is 4, okay, and A times AD minus BC is going to be 1, but C is 0, so AD is 1, okay. So this is, so you see this is going to be 4 minus 4, so it is going to be 0, so A will be equal to D, okay, and so A is a translation, it is a translation, namely Z going to AZ plus B by D which is A, which is just the same as Z plus B by A. Okay. So actually in this case you can see it, you do not have to do any conjugation, alright, to if A is parabolic and infinity is the only fixed point, then it is already a translation, alright. If in the case, so in the case when Z0 is not equal to infinity, okay, then you choose B like this, you choose B like this, BA B inverse continues to be parabolic with infinity a fixed point, infinity the fixed point, okay, because you see the property of a Moebius transformation being parabolic or elliptic or loxodromic or hyperbolic is not going to change when you conjugate it. That is because that property is defined by looking at the value of trace squared of this matrix, and you know the trace of a matrix is invariant under conjugation. That is, you take a matrix, you pre-multiply it by an invertible matrix and post multiply it by its inverse, okay, the inverse of the pre-multiplied matrix, then the trace continues to be the same, okay. So if I take any Moebius transformation with any of these properties and if I conjugate it, I will continue to get a Moebius transformation with the same properties, okay. If I conjugate a loxodromic transformation, I will again get a loxodromic transformation. If I conjugate an elliptic transformation, I will again get an elliptic transformation, and so on. So since I have assumed A is parabolic, BA B inverse continues to be parabolic, okay, and infinity is a fixed point, so you are in this case. So BA B inverse is a translation, okay. So this gives you the proof of this, another proof of the statement that I was giving you in the last lecture, that you know for a parabolic for a transformation to be parabolic, it should be conjugate to a translation, okay. So the last time I gave you I was looking at a different proof because I wanted to show to you that if you try to solve for B so that BA B inverse is a translation, say even translation by 1, it forces the condition that the trace square should be 4. So this is another direct way of seeing that, right. Now okay, so this is the situation when there is only one fixed point, but let us assume that there is another fixed point. Suppose A is not parabolic, okay, so then it will have another fixed point, okay, then it has another fixed point, say Z1, okay. So Z1 is another fixed point for A, okay. So that means, you know, we are now in these remaining cases. So A has to be either, it has to be loxodromic or elliptic or hyperbolic, okay, and we want to see what kind of form A has, alright. So you see, if it has another fixed point, say Z1, you will see that well in either of these cases I can always find a B such that infinity is the first fixed point, okay. So again choose B as before, so that BA B inverse has infinity as the first fixed point, okay, that I can do. And mind you, of course, if I am in this case I have to choose B to be identity because I do not have to conjugate at all, okay, I do not have to conjugate if I am in this case. If already the first fixed point is infinity, I do not have to conjugate, I can take B equal to identity. If the first fixed point is not infinity, then I have to conjugate so that the first fixed point becomes infinity, okay. So if I take BA B inverse, infinity will be the first fixed point, but now the second fixed point is changed to B of Z1, okay. the second fixed point is B of Z1. That is because you see if I calculate BA B inverse of B of Z1 I will get BA of Z1 which is B of Z1, so I will get that this is a fixed point, okay, that is obvious. Alright, now what I am see I have already moved by a conjugation I have moved one fixed point to the point at infinity, okay, and you know what I am going to do, you can guess this, I am trying to the other fixed point is not the point at infinity, it is a different fixed point, and you know I will again do a conjugation, move it to 0, okay. So I try to bring A to a form of a Moebius transformation which has two fixed points, namely 0 and infinity, okay, so that is what I am going to do. So for that to make this fixed point to go to 0 I just have to translate by minus of this, okay. So let C be, let C of Z be just Z minus B of Z1, okay, Z minus B of Z1. So this is translation by minus B of Z1. So what happens is if I take C B A B inverse C inverse, okay, if I take this Moebius transformation, alright, which is incidentally also the same as CB A CB inverse if you want, these are the same, CB inverse is B inverse C inverse, right. If I take this Moebius transformation then you will see its two fixed points are going to be 0 and infinity, okay. Mind you, C here, C as matrix is you know its translation by minus B of Z1, so it is going to be 1 minus B of Z1 0 1, which is already in SL2, this is a translation by minus B of Z1, okay. And what is C inverse? The inverse of a translation is just translation by the negative of the vector that you originally translated with. So C inverse as a matrix is just going to be 1 plus B of Z1 0 1, this is what C inverse is going to be, okay. The inverse of a translation is just another translation, right. So if I take this then I will get two fixed points 0 and infinity, okay. So so you see CB A CB inverse has the form Z going to lambda Z, okay. If infinity, you see if infinity is a fixed point already C is 0, okay, and it is and it becomes your Moebius transformation becomes A by D times Z plus B by D, Z going to A by D Z plus B by D, alright, that is what this means, Z going to A by D Z plus B by D, it comes to this form, alright, if infinity is a fixed point. And now if I say that 0 is also a fixed point, this constant term cannot come because 0 has to go to 0, that means B has to be 0, okay, and if B is 0 then it is just going to be Z into some complex number, okay, and that complex number you can I am calling it as lambda, okay. So the moral of the story is you take a Moebius transformation that is not parabolic, then you can always do a conjugation and bring it to this form, okay. Now the question is you can guess what I am trying to get at, I am trying to see what properties of lambda will make it, you know, loxodromic or elliptic or hyperbolic, that is the point, okay. And it turns out that there are very simple conditions on lambda that can tell you whether this is, you know, one of those types. So let us look at those situations. So yeah, so you know the matrix representative of z going to lambda z is, well, you know, it will be square root lambda 0 0 1 by square root lambda. Okay, see, if I write lambda z just as a matrix, I will simply get lambda 0 0 1. If I write z going to a z plus b by c z plus d as a matrix a b c d, then z going to lambda z, the matrix, if I write as a matrix, it will be just lambda 0 0 1. Okay, but the determinant of that matrix is lambda. Okay, it is not an SL2C representative, because I am only looking at SL2C representatives for my calculations, especially when I do this trace business. Okay, so to make it an element of SL2C, I take a representative like this. Of course I can also put minus, I can take minus root lambda minus 1 by root lambda, and mind you, root lambda is 1 square root of lambda. There are two, in general there are 2 square roots of lambda, and I take any one square root and use the same square root here in both cases, alright. And mind you, note that lambda is not 0, it is not 1, because you know, if lambda is 0, then that is not a Moebius transformation, it is just the 0 map. Okay, it is not a Moebius transformation. And if lambda is 1, then this is identity. If CBA CB inverse is identity, so I think the inverse has been wrongly put, it should be put outside. Okay, if you conjugate a matrix and you get identity, then that matrix itself has to be identity. Okay, because you can unconjugate it, and on the right side, because you have identity, it will continue to be identity. Okay, so this A not being the identity will tell you that lambda is not equal to 1. Okay, A not equal to identity implies lambda is not equal to 1. So you see, the lambda values lambda equal to 0 and 1 are forbidden. Okay, lambda can only have values other than 0 and 1. Alright, now let us so you see, when I gave this definition of so I have rubbed it, the loxodromic condition, so let me write it here, let me rewrite it here. Loxodromic if trace squared a b c d, which is a plus d the whole squared, is in C, is a complex number, not a real number in this interval. So this, see, I am considering this as a subset of real numbers. Okay, so if the trace squared does not take a value on this segment, okay, then that is my definition of loxodromic. Alright, of course trace squared is not 4, because there are 2 fixed points and it is not parabolic. Alright, so in all these, so let us look at these 2 cases. You see, in these 2 cases, you see the trace squared is real. Okay, and the loxodromic case with which is not hyperbolic. Okay, because hyperbolic also implies loxodromic. The loxodromic non-hyperbolic case is the case when your trace is that is a condition when the trace does not lie in the segment. So what I am going to do is I am going to first look at the condition that trace squared is real. Okay, so you see trace squared A, okay, is real if and only if, you know, trace squared A is the same as trace squared of this. Okay, trace squared of CB A CB inverse is real. Okay, but CB A CB inverse, the matrix is this. Alright, and what is the trace? It is root lambda plus 1 by root lambda, that is the trace, and the trace squared will be root lambda plus 1 by root lambda the whole square. So that is root lambda plus 1 by root lambda the whole squared is real. Okay, this is what you will get. I mean, this is the condition you will put if you want to study something that is elliptic or hyperbolic, right. So but what is this? Well, this is just if I expand it, it's lambda plus 1 by lambda plus 2, this is real. Okay, so well, let us investigate this situation. So let me rub this off. So I'll keep this part as it is, all right, and I'll continue here because I would like you to keep this definition in mind. So you see, so of course lambda plus 1 by lambda plus 2 is real if and only if lambda plus 1 by lambda is real. Okay, so that is lambda plus 1 by lambda is real, all right, and what is the condition? This happens if lambda plus 1 by lambda is equal to lambda bar plus 1 by lambda bar. You know, a complex number is real if and only if it is equal to its conjugate, and then I can collect terms. I will get lambda minus lambda bar is equal to 1 by lambda bar minus 1 by lambda, which is again lambda minus lambda bar by lambda bar, and you know lambda bar is just mod lambda the whole squared. If I cross multiply, I will get lambda minus lambda bar into mod lambda the whole squared minus 1 is equal to 0. I will get this condition. Okay, if I collect terms, lambda bar is mod lambda the whole squared. So when will trace square a plus d be real? Trace square a plus d will be real, I mean trace square of a which is a plus d the whole squared will be real if and only if this transformation that I have gotten after conjugation, which is essentially z going to lambda z, the lambda satisfies this property. Either lambda is equal to lambda bar, okay, which means lambda is real, or mod lambda is 1. Okay, so let me write that down. Okay, so you get these two conditions on lambda. Okay, let us investigate these conditions. Suppose mod lambda is 1. Okay, we will show that mod lambda is 1 is the case when it is elliptic. Okay, why is that true? Well, you see, so you know lambda, you write lambda as you know mod lambda e power I argument of lambda. Okay, and well 0 is less than argument of lambda is less than 2 pi. Okay, so you have the argument should vary over an interval of length 2 pi, right, and of course I exclude 2 pi and I include 0. Okay, now you see notice that argument lambda equal to 0 is not allowed, because you know if argument lambda is equal to 0, alright, then I will get lambda equal to mod lambda, so I will get lambda equal to 1, okay, but lambda equal to 1 is not allowed. Okay, so argument lambda is equal to 0 implies lambda equal to 1. So you see 0 should be strictly less than argument of lambda, strictly less than 2 pi. Okay, so what happens? So let me write this as so lambda is e power I theta, okay, where theta is argument of lambda. So I am in this case. Okay, and look at that quantity. Trace squared a is just e power I theta plus 1 by e power I theta plus 2, okay. So it is going to be, this is cos by de Moebius formula, this is, you know, this is cos theta plus I sin theta, this is cos theta minus I sin theta, so I will get 2 2 cos theta minus 2 plus 2, alright, and you see this this quantity, you know, cos theta is bounded by 1, alright. So so the first thing I need to say, so I just want to say that this is, in any case this is less than or equal to 4, okay, this is less than or equal to 4, and mind you so I want to make the statement that this quantity is going to lie between 0 and 4, it cannot be equal to 4. So you see, if this is equal to 4, okay, then you know cos theta has to be 1, okay, but cos theta will not assume the value 1, okay. So in fact strictly less than 4, okay, and I claim that this quantity is actually positive, is greater than or equal to 0, this quantity is greater than or equal to 0 because you know why is that so, that is because I think that is also quite obvious. I mean you know cos theta at the minimum can become minus 1, and in that case I will get 0. Cos theta is always greater than minus 1, greater than or equal to minus 1, and I am adding 2, I am multiplying it by 2, so 2 cos theta is greater than or equal to minus 2, and if I add 2 it is always greater than or equal to 0. So this implies that you know 0 less than or equal to trace squared a strictly less than 4, and that will tell you that a is elliptic, okay, that is the condition. And mind you, what it will actually tell you is that this is elliptic, but then I told you by after conjugation the ellipticity does not change, so the original transformation A that you started with is also elliptic. So the moral of the story is, you take a non-parabolic transformation, you conjugate it so that it becomes z equal to lambda z, so it becomes z going to lambda z, and if mod lambda is 1 then it will be elliptic, okay, and the converse also holds. If this is elliptic then mod lambda has to be 1, okay. So how does one see that? So let me write that down. Conversely, if A is elliptic then mod lambda is 1, okay. If A is elliptic I claim mod lambda is 1. Why? Because you see because of the following reason, for A elliptic means, you see 0 less than or equal to lambda plus 1 by lambda plus 2 less than or strictly less than 4, alright, that is what it means. It means this is real, lambda plus 1 by lambda is real, okay. So if it is elliptic, what is the definition for elliptic? A plus d the whole squared is real, alright, and a plus d the whole squared turns out to be this is real. So lambda plus 1 by lambda is real, and its value lies between 0 and 4, 0 included, 4 excluded. This is the condition for it being elliptic, okay. Now from this you can conclude that mod lambda is 1, okay, and how does one show that? I think it is quite obvious. So you know what will happen, lambda plus 1 by lambda real would mean that you know either lambda is equal to lambda bar or mod lambda is 1. Okay, of course we are trying to prove mod lambda is 1. So what we will have to do is you have to exclude the case when lambda is real. Suppose lambda is real, so this is the case you have to study. Okay, alright, so we will show it cannot happen. We will show it cannot happen. Why? Because you see you take the function f of x is equal to x plus 1 by x plus 2, okay, take this function, then of course x not equal to 0, then you will see that its derivative is you know 1 minus 1 by x squared, okay, and therefore critical points or turning points of the graph of the function are going to be are x equal to plus or minus 1. I have to equate this to 0, alright, and the second derivative of the function is going to be 2 by x cube. The second derivative at plus 1 is positive, so at plus 1 I have a minimum, so f of plus 1 is minimum for x positive, okay, and the f of, if I take the second derivative at minus 1, okay, then I will get a negative value, so I will get f of minus 1 is maximum for x negative, okay, and what are the values? So you see, so x positive implies f of x is always greater than f of 1, greater than or equal to f of 1, okay, and f of 1 is 4, okay, and so x positive x not equal to 1 will imply f of x greater than 4, okay, and x negative will imply f of x is less than or equal to f of minus 1, okay, which is 0. So x negative x not equal to minus 1 will imply that f of x is strictly less than 0, okay. So this is a very simple calculus computation, but it is very helpful to us. So you see, if now you see if lambda is real, okay, then there are two cases, lambda can be either positive or negative, alright, and well my situation is that so what is given here is that f lies between 0 and 4, okay, so if I instead of x, if I plug in lambda, if I take f of lambda, then f of lambda is either greater than 4 or it is less than 0 if lambda is real. What is the upshot of this? If x is real, the expression x plus 1 by x plus 2 is either greater than 4 or it is less than 0, okay, provided x is not allowed to take the values plus or minus 1, alright. So that will give you a contradiction to this case, that so lambda cannot be real, so lambda cannot be real, and lambda cannot be real, the other case will be that lambda has to be 1, mod lambda has to be 1, okay. So what we get is that the transformation is elliptic, okay, if and only if after conjugation to make it into the form z going to lambda z mod lambda is equal to 1, So mod lambda equal to 1 is the condition for it to be elliptic, alright. Incidentally there is the other case when lambda itself is real, okay, that also has been taken care of here if you watch carefully, okay. So let me put this in a box, okay, I will put this in a box. I mean this is a rather simple computation but it is very helpful. So you see let me go back here and look at let me look at the other cases. So suppose A is not elliptic, okay, suppose A is not elliptic but you see lambda but trace squared A is real, alright. Suppose A is not elliptic and suppose trace squared A is real. So then mod lambda is not equal to 1 because A is not elliptic, because we have proved just now that mod lambda being 1 is exactly the case when A is elliptic. So mod lambda not equal to 1 will imply that lambda is real, okay, you will get the case that lambda is real, alright. Now you see if lambda is real, okay, you look at this this situation, okay. So I have to say something. So there are two cases, either lambda is positive or lambda is negative, okay. If lambda is positive, alright, then you know trace squared A is just lambda plus 1 by lambda plus 2 that is greater than 4 here. If x is greater than 0 and x is not equal to 1, then x plus 1 by x plus 2 is greater than 4, okay. So trace square A becomes greater than 4 and that is the condition for A to be hyperbolic, okay, which means A is hyperbolic, okay. Conversely, if A is hyperbolic, alright, then I claim that the condition is lambda is greater than 0, okay. Okay. Conversely A hyperbolic implies lambda greater than 0, okay, you get that. So and why is that true? Because you see if A is hyperbolic, alright, then the condition is trace squared is real, okay, and trace squared is real will mean either lambda is r, mod lambda is 1, but A is hyperbolic and so mod lambda cannot be 1 because then if mod lambda is 1 A is elliptic, alright. So lambda has to be real, and if lambda has to be real and you have this condition hyperbolicity condition that lambda plus 1 by lambda plus 2 is greater than 4, then lambda has to be positive, because if lambda is negative, lambda plus 1 by lambda plus 2 is negative, okay. So the condition that A is hyperbolic is controlled by this lambda being real and positive, okay. So Z going to lambda Z should have the property that lambda is real positive, that is the condition for A to be hyperbolic, okay. So we get that. So I have this the other case, lambda less than 0, lambda is negative, we have seen that we have seen here that lambda plus 1 by lambda plus 2 is less than 0 and therefore you are in the loxodromic case, okay. So if lambda is less than 0, trace squared A is negative, so A is loxodromic. So the upshot of this whole discussion is the following, okay. Lambda mod lambda equal to 1 if and only if A is elliptic, okay. Lambda real, lambda positive if and only if A is hyperbolic, okay, and mod lambda not equal to 1 if and only if A is loxodromic, okay. So these three simple conditions will allow you to distinguish between elliptic, hyperbolic and loxodromic transformations, and somehow we have arrived at these conditions by start looking at the trace squared, okay, which was originally used to define these things, alright. So we will continue in the next lecture.